we're going to start with the safety systems session. Actually, here we are going to see just, I would say we are just going to scratch the surface, so just a really brief overview about, safety systems based on our S7 controllers and configured in TA portal. So we see just a few, few concepts, so basic concepts, and also the options that we have available in our portfolio to address applications where safety is a requirement. So when you talk about safety, so the main goals are to protect people and even protect the installation, the equipment, the machine itself, sometimes even the environment, against any hazard or some hazardous situation that could be caused by the equipment's failure. So some particular function of the equipment fails, and that might cause injury, that might cause damage to the equipment. So whenever such situation or such equipments are designed and required, and you identify such situations, then a safety system is required to address those situations. So, and the reasons could be that there are laws, or so that make it mandatory for some types of equipment or machines to have safety systems. But sometimes the reason is it's also economic, because if something happens with the operators or if with the machine itself, with the installation, so definitely there'll be some penalties, or there's a loss of production, or increased costs in terms of repairs. So that's why when we identify that there is a requirement, we use safety systems. So again, just showing you what would be the use, so to prevent injury, or even worst case death of operators or people around, or damage or even destruction of a particular equipment or machine. And as a consequence, losses in terms of production, in terms of non-availability of the equipment, and so on and so on. So that's why there is a requirement for safety systems. There are some, several standards that cover, the design and use of safety systems, and in different areas. So there are some general standards that cover, safety in different, in different sectors. Could be in terms of discrete automation, process automation, and so on and so on. And there are some specific ones that cover specific applications, and even to the point that are also standards that cover how to design and develop safety devices. So for us here, I just put a really short list of the ones that you might see here and there whenever you see, for example, the specification of a device that's used in safety systems. Could be a controller, could be a sensor, could be an actuator, for example. So they'll be certified according to some standards. So these standards that I show here are maybe some basic ones that you might see most frequently whenever dealing with these devices and equipments. But there are much more standards that are used in different areas for different applications different types of devices. And just as an apart, so for example, if you take, one of our controllers and you say a fail-safe controller, and you check the certificate for safety, or they mention function safety or machine safety. So you see that the certificate is issued. So the tests are done according mostly to the standards that you see here in your screen. So that's just a small detail that if you are curious or if you need, you see that in the certificate, these are the standards that are mentioned that are used to certificate or to provide approvals for a particular system or device. And then in terms of, let's say, when there is a requirement of the safety of a safety system, actually that need comes based on a particular process. So let's say you're building a particular piece of equipment, a particular machine, where you see that there are some points that could cause, or that are, bring some dangers to the operator or even to the installation itself. So to identify, to check if you need, a safety system applied to that particular piece of equipment. So there is a particular procedure based on the available standards that you need to assess all the risks involved in that particular machine. So you identify what kind of dangers or kind of hazards are there in the machine, and then you need to evaluate the level of the risks. So it means that, say, how frequent is the risk is there, or what's the severity of the damage that it can cause, for example. And based on that assessment, if you find that there are, say, unacceptable levels of risk, then you, based on some criteria, you define, okay, what kind of safety system or safety device I need to use. For example, as a simple measure, there are some rotating part that can cause, say, injury to someone operating the machine. As a simple measure, you can just put a cover on that rotating part, and then say you reduce the level of risk to an acceptable level. So then you can have your machine operated in a more, more safe way. But sometimes, of course, there are some measures that you apply that might cause might reduce maybe the performance of the machine, or might make the equipment more difficult, for example, to operate. So then you need to find other measures to reduce the risk, but at the same time not, reduce the performance or the usability of the equipment or the machine. So this is all done in a process where you identify the risks, you design and apply some system to minimize or reduce the risk. And then, of course, in the end, you need to have some proof that those measures are enough to reduce the levels of risk. So this is, the complete, process of evaluating and designing a system that can reduce the risks of accident or injury on the equipment or the machine. So one of the, the most, one of the terms that are used are the safety levels, and you can all the cases whenever there is a requirement for a safety systems, especially based on an electronic equipment, even other devices can be also assessed like that. But let's say you're having an inquiry asking, okay, I need, let's say, a CO3 controller or a CO2 device. So this is one of the ways of, let's say, evaluating the safety level required for some equipment. And then that's defined in the standard how to actually get to that, to identify. Sorry. Could you mute your microphones, please? Okay, thanks. So based on the standard, so we can define what's the, based on the assessment of the risks and the level of the risks. So based on that assessment, you can come to the level, let's say the safety level required to reduce the risks. And then that's done based on the standard. So for example, to get, when you say, okay, I need a CO3 controller or a controller that can be used in a CO3 application. So we get to that information that I need a CO3 application based on some criteria. For example, based on the IEC or EN 62061 standard. Actually, it's the same criteria that we have on the 6158508. So based on the severity of, the damage or injury that can occur from a particular risk, and also based on other criteria on, let's say, how frequent is that risk there, or how probable that can occur, or even is that avoidable or not based on the current design of the equipment. So based on these criteria, we can come to the information that, okay, I need for this particular application, I need a CO2 system to handle or to reduce the risks. Or sometimes I can get to, depending on the measures that I take, I can come to a point that, okay, I identify that I don't need a safety system, so a standard system, control system can handle or the equipment. So based on the standard, you can identify, so by the assessment, which the safety level, and based on this particular standard, is the SIL level, so safety and integrity level. So which level, so what what safety level I need in terms of the equipment to be applied to the machine or to the equipment. Also based on another standard, that's actually the ICEN standard are the mostly used, but even the ISO standard also provides you a way of accessing or say defining the safety level. Here we are talking about the term is SIL, so SIL 1, 2, 3. Actually, there is a SIL 4, but not applied to machine safety. But when you go into, let's say, process safety, then there is another level, but it's not applied here. On the ISO standard, we have, instead of 4, have 5 levels, and they're assessed in a slightly different way, but the results are maybe similar. And again, so when you check our devices or our, for example, a controller or an I/O system, you see that the certificates issued, they are based on different standards. So including, so you see that, for example, an S7 controller, a fail-safe controller, is certified for applications up to SIL 3 level and performance level E. That's the highest level based on the ISO 13849 standard. So they are certified according to different standards. So whenever the user, say, uses one particular standard or another, so they can use the same system as a safety system. And then, in a nutshell, so just to provide an idea, so when we're talking the highest risks available, the highest, say, security, safety level of CO3 or performance level E, and so on, just to give an overview between them. So when you're talking about the different types of, asset or the use of different standards, so performance level and CO level, so we can relate them. They are different standards, but there is some common ground. So, for example, one of the common grounds that are between those standards is what we call the probability of dangerous failures, either per hour or on demand. So, it depends on different cases. So, this is another term that you'll see quite frequently when you're designing or selecting a safety system. So this is a number or a figure that's provided by the manufacturer of the particular device that gives you an idea of the probability of a failure or a dangerous failure over time, normally per hour. And then also it's a criteria for you to identify that a particular system is according to, I don't know, particular say CO2 or CO3 level, performance level D or E. So those numbers will give you based on a particular interval, a particular level of the PFH or the probability of failure, if the system can be applied in a CO2 or a CO3 application. So that's another criteria that's used. But here is based on the equipment that you do. So first, based on the risks, you define the safety level. And then when you select and design and use or select a particular set of devices, so you need to check if those devices fit in the safety level that was defined. So the PFH is one of the criteria or one of the figures that are used in the calculations to check if that particular configuration fits in the requirement of that safety level. Okay, so this is just a few, concepts and terms that are common and frequently you see whenever there is any application for safety systems. Then starting going towards the portfolio or the systems that we can offer within our portfolio for safety. So I would say in a classic approach, for example, you could have let's say an application where you have, let's say, a standard control system based on a standard controller, standard IOs, and other devices. And then if you require the safety system, that can be done in a separate way. So with a separate, maybe if it's a small one, can be just a safety relay, or it can be a programmable safety relay, or it can be even a separate safety controller. For us, we can do say all at once. So it means that you can have a controller that can handle the standard and fail-safe part of the equipment control. We have say sensors and actuators that also can be used in the safety applications. So that's what we call safety integrated. So that concept we have for a long time now, and currently we have the options based on all the control systems available in TA Portal, for example, be it S7-1200, 1500, E2SP, IO systems. So all of them integrated and available within TA Portal. So this is one example for an S7-1500 based application, but also if you're talking about maybe smaller systems with, let's say less requirements, so maybe less number of safety functions, then you can also use an S7-1200 fail-safe. So fail-safe CPUs and IO modules are available also for S7-1200. So when we're talking about safety, so it means that we have the hardware, so we have the controllers, we have the IOs, but at the same time, we need the engineering to, to configure and develop the application, a fail-safe application. So in TA Portal, of course, you're going to need step 7 to configure the controller. On top of that, you need also an additional package, the safety, in 2 sizes. So safety basic, if you're only configuring S7-1200 based applications, or the safety advanced, if you're configuring the large controllers. It includes also 1200, but 1500 SP controllers, and even if needed, 7300-400F controllers can be configured in TA Portal using the safety advanced together with step 7. So another apart. So when I mentioned about the certificates of our controllers, actually, when you check the certificate for an S7-1200, 1500, you most probably won't be able to find a particular certificate, because the certification is done based on the whole system. So the certificate is based not only on the hardware, but also on the engineering, the instructions available, so the fail-safe instructions available within the engineering. So you'll find, for example, a TUV certificate for related to, functional safety. So that includes the whole hardware, but also the engineering tools used to configure and program that particular hardware. So that's why it's always a combination of the hardware part and the firmware and engineering software as a complete system to develop a safety-related application. So when you start talking about the controller part, on the controller side, so the hardware, so basically, also a safety application has, a similar concept of a standard one. So we have, so you need to read some inputs from the field somehow, have some processing, and have a response accordingly. But because of the requirements of safety systems, that is done in different ways. So there are additional functionalities available in a safety system that can detect, let's say, dangerous situations and shut down the system into, say, a safe status, so to avoid, let's say, any kind of damage or any kind of injury to people. So, and that is done, for example, with particular hardware, let's say fail-safe CPUs, fail-safe IOs. Even in terms of the sensors and actuators, we can use standard sensors, but it needs to be combined in a certain way that you can reduce the risk of, let's say, a dangerous failure. So, for example, if you have only a single input being read from a sensor, if that sensor fails and say you don't have a mean to detect that failure, that can cause a dangerous state, and that dangerous state can cause injury and damage to the machine, or injury to a person, for example. And even in terms of the actuator, the same way. So if you don't have a means to guarantee that the actuator, say the probability of dangerous failure is reduced on the actuator side, also that can cause, say, a dangerous situation. So how can we kind of mitigate or increase, the level of safety, or say how to, let's say, to detect this additional, so these cases of dangerous situations. So, for example, the fail-safe inputs, they have extra, let's say, diagnostics that can detect that the input itself, or maybe the sensor, has some issues. If there is maybe a short circuit, or if the sensor if it's say maybe two sensors, you have a discrepancy when they actuate, for example, and they have means even to detect if the failure is within the hardware itself. So check if the hardware is consistent. If something is wrong, let's say stop the system, for example. Same with the CPU. Same with, for example, some I/Os. Same for the outputs of the system. So this is the more, in terms of the hardware, these are the biggest differences between a standard system and a fail-safe one. So these are the additional measures to be able to detect failures and stop the system in a safe way, so to avoid further damage or injury. So starting with the controller itself. So in the beginning, so the initial approach, so if for a fail-safe controller, actually was done by duplicating the controller and the I/Os. So it was, let's say, a redundant controller, but the idea here was not to say increase the level of availability, but also to increase the level, but to increase the level of, say, reliability. So it means that both controllers are running exactly the same program, and then they're processing and comparing the program. So comparing the inputs, comparing the code, say, that being run, comparing the outputs. If any discrepancy was detected, the system would shut down and stop until that particular issue was fixed. So that was the, let's say, the initial, let's say, the first generation of safety systems. One example here is based on an S5, so redundant controllers. Next generation based on S7-300, 400, and nowadays S7-1200, 1500. Actually, we use a single CPU, but with different mechanisms to guarantee that if there is any particular discrepancy during the program processing, it can be detected and the system will shut down to avoid further problems. And that is done by having what is called diversity. So actually, the CPU runs the program in two different ways. So they call, let's say, a normal, a normal program and a coded program. I'm not going into details of how this code is done or not, but in different ways. And then that's compared in the end. And also that is done in different points of time. So it runs first the normal program, then after that runs the coded program. In the end, it compares both, and then if any difference or any discrepancy is detected, the system shuts down. So just, a few slides just to kind of give a brief idea. So in terms of diversity, so there is a standard and the coded program. So the program is running different ways. Not exactly sure how it's done, but it's done like that, and in at different points of time. And then after they run, so in the end they compare, and then if there is any difference or any discrepancy detected into this comparison, the system will shut down to avoid further problems. And so, for example, here it shows how it's done. So the CPU executes the user program first, then the coded program, and then compare the results, so in a sequence. So that's one of the reasons that if you see, if you compare the specs of a fail-safe CPU to a standard CPU, so the same model, you see that in terms of the performance, they are usually the same, except for the amount of, say, memory, so work memory, because the CPU because of the use of the coded user program. So say additional memory is used to run the program. So that's why most of the fail-safe versions of the CPUs, they have slightly higher say memory size. So that's the reason why you have a bit more memory for those CPUs. And then in terms of the portfolio, so the whole portfolio of controllers within TA Portal, we have the standard options and have fail-safe options, starting from 1200, 1500, Ethernet SP CPUs, and even the software controller, we have fail-safe options. So in terms of the S7-1200, so for smaller applications, less complex, or with less number of, say, safety functions. So we have 3 CPUs. We have some fail-safe IOs. Actually, one interesting point here is that the built-in IOs on the CPU, they are not fail-safe, they are standard IOs. The reason behind that is that if we had, let's say, fail-safe IOs directly on the CPU, let's say, in terms of development and certification of the device would take much longer. So that's why we decided to keep the built-in IOs on the CPUs standard and have additional fail-safe modules that could be used in fail-safe applications. So in case of the 1200, some fail-safe digital inputs and outputs are available. But again, if there is a need, most probably because it's a small system, but if required, also additional fail-safe IOs can be added over, for example, Profinet, so in a distributed IO system, for example. Then we get into the onto the advanced controllers, so SM1500, again here, so the whole portfolio of standard CPUs have, say, a fail-safe version. So that's an improvement compared to the previous generation of the S7-1300, for example, that we had just a few of the CPUs, they had fail-safe versions. So here, starting with the smaller CPUs up to the biggest one, we have standard and fail-safe CPUs. So, and also mentioned the software controller also has a fail-safe version. In terms of the distributed controllers, so based on ET200 systems, also again, so fail-safe versions.
Zari?
Yes.
So fail-safe versions of the CPUs available, let's say the same. Standard CPUs have the same, have also available, let's say, fail-safe versions. And then we start talking about the IOs. So, the safety system, you have the controller, but we need to have means of, say, reading inputs from sensors and also having the outputs for the actuators for the fail-safe application. So, starting with the ET200 systems, so Ethernet SP. So with Ethernet SP, we can use fail-safe IOs, of course, with the fail-safe CPUs, 1510F SPF CPU or 1512F CPU. And in terms of IO systems, or distributed IO systems, so the Profibus IM and also the Profinet IMs, the standard and high feature, all of them support fail-safe IOs. And you see here that of course, there are differences between them in other aspects, but even for maybe a simple application, so using a standard IM can be, you can use for, a fail-safe application. In terms of IOs, you can expect at least to have digital inputs and outputs, so fail-safe versions. So, for example, there is an 8-channel digital input available for the, a fail-safe 8-channel for the SP. And here's an example of an emergency stop according to CO3 or performance level E. So just the wiring. Here we are talking about let's say, in terms of the I/O channels, it's one out of two evaluation to achieve that level of that particular safety level. So meaning that you are using two channels, two physical channels as one channel within, let's say, within the application. So evaluated a single channel, and then with this configuration, we are able to achieve, let's say, the highest safety levels. There are some other simpler configurations, especially if you are going with, let's say, lower safety levels, to be CO1 or CO2, that you might not require, let's say, using two channels, so one channel is enough to achieve that particular safety level. So one example, emergency stop. Another example, for example, using, say, safety barriers or other, I think these are, so door sensors, for example. So again, using, so for applications reaching, let's say, a CO3 or performance level E safety level. And then, for example, this is one of the features that you find in terms of, say, diagnostics in a fail-safe DI and not in a standard one. For example, this chatter monitoring that can detect if, let's say, a particular input has some, whenever we switch on or switch off, or especially switching on, there is some, how can I say, some, pulses until the input gets stable. So that can be, for example, detected from an FDI, and then, if required, say, detecting, say, a particular hazardous situation, it could, say, shut down the system. So in terms of digital outputs, there are a few digital outputs, different types. So transistor, relay outputs. Even there is a particular power, say, fail-safe power module that can be used in certain applications to maybe simplify whenever a particular CO level is required. But for example, the FDQ, so that can be used again up to CO3 or PLE. So one particular, say, wiring according to the requirements of the CO3 application. So, and here you see that for CO3, there's a requirement of two. In this case, the two actuators are actually, they're common contactors. Actually, you can see, you can find this information in the manual. But the reason that you need, let's say, two contactors here, for example, in parallel, there are some reasons behind that. Let's say to reduce the probability of failure, because let's say the contactors, they have a particular probability of failure over time, and then according to the standards, there are some levels accepted that can be used for, say, a CO1 application, CO2 or CO3. So here the use of two contactors is actually to reduce this probability of failure to a lower level that is accepted in say, a CO3 application. So that's why you see, say, two contactors being used in parallel for this particular safety level. Lower safety level, you might be able, of course, you need to do some calculations, perform some calculations to see if you can reach that level. So you might be able to use a normal contactor, or if you're not using, say, standard contactor, so if you're using, for example, already, say, certified or qualified, you're using a particular certified or qualified actuator, so you don't need to to perform any calculation to see if that fits in your application. You know already, because you get the figures in terms of the safety level, or even say probability of error of a failure directly from the supplier. So again, additional measures to detect, say, dangerous situations. So, for example, for the FDOs or FDQs, we have some tests. For example, one of them is the dark test that actually, when the output is switched on, so internally the model briefly switches off one line, say the positive line, and also briefly switched off the, say, the ground or the 0 volt. So with this, say, test, you can detect, for example, internal errors, meaning, for example, if you are switching on the output, but then you switch, say, you disconnect the output, but you are still getting some value. So it means that maybe there's a short circuit, an internal, or even an external short circuit that is providing, say, maybe 24 volt or 0 volt directly to the actuator, to the load. So these are additional measures that you find in this FTO model that can detect those situations, and as soon as they are detected, it will, say, maybe I wouldn't say shut down completely the system, but what we call, they will, say, passivate. So they will, say, more or less disable that particular output until that error or that failure is corrected. So even other tests are available. So switch on test in a situation where the load is, say, the output is off. So to check if there is any abnormal situation. So light test. So you see that these are the additional measures or the additional diagnostic features that you find in this fail-safe IOs that help the system be able to detect dangerous situations and take measures to avoid, say, damages and or say injuries overall. So other models available. So FDO. So there's a relay output also. The power module, actually, it's an interesting one because you know that the standard Ethernet speed doesn't require power modules. But here the idea is that you can use, it's a fail-safe power module that can be used especially in lower, let's say, C-level applications, C2, C1, where you can have, let's say, a safety shutdown by using normal digital outputs. So actually the F power module is the one that's going to handle the shutdown. So in this case, you can, say, simplify and even reduce the cost of overall of the system by using, instead of having, say, of using FDOs in a up to CO2 application, safety shutdown, you can use an FPM and then standard digital outputs for the shutdown. So that's one of the main uses of the FPM, the power module. And we have also for the SP some fail-safe analog inputs. So voltage and current available. So we didn't have that in the past. Now we have for some time. So that's the idea here. And then, so there are other devices, for example, motor starter. If you want to, so instead of using a standard, contactor, you can use already as a qualified actuator that can be used up to a CO3 application. Also, ASI safety, so they can have the safety devices also on ASI. And for the S7-1500 IO modules, also used on the Ethernet MP, there are some fail-safe modules currently FDI and FDO available. So just in a nutshell, how the safety system based on our controllers and IOs run. So it's running, running, say, different diagnostics at the same time. Anything detected, so the model, so an FDI or FDO is passivated because of a particular error, and then when that particular error or failure is fixed, so we can depassivate and have it. So in that way, the system have additional measures to detect and handle, I say, errors that can lead to dangerous situations. And then just to finalize, so there are some tools available. There's a tool available, say, to evaluate a particular system and calculate what's the level of the safety level required for that application. And there are, I mean, some examples, project examples available for fail-safe applications. So that's all from the safety part.